Remember your number.
Are we counting how many people are in the lecture?
Well, unless I made a mistake, you're 16. Alrighty. So, got quite a bit to get through today. Because we're going to finish off this lecture on arithmetic circuits, and we're going to make a start on the lecture about combinational circuit components. And I'm hoping that that will bring us sort of in line with where you're at it in the labs. I know you're probably a little bit ahead in the labs over what I'm talking about in the lectures, but I don't think that's a huge problem. We outlined the objectives that we were going to talk about for this lecture on Friday. Today, we're going to be sort of focusing a little bit more on VHDL for specifying arithmetic circuits on the one hand, and then there's this rather chunky topic at the end about how to boost performance for adders. So you will recall that we talked about this slide last week. This shows in blue a full adder component, or the description of a full adder, which, recall, takes 3 bits as input, 2 bits from the number that we want to add together, x and y, and a carry in, and produces a sum and a carry out, because effectively we treat these 3 bits in unary. We know the sum can be anywhere between 0 and 3, and we need 2 bits to represent the sum, namely a single bit that we'll call the S bit in this bit position plus a carry out. And then this pink design for a 4-bit adder was presented, which makes use of this full adder as a component in order to wire together 4 instances of that component by essentially establishing a relationship between the inputs and outputs that we have for this component, or this design, this higher level design, and the lower level 4-bit adders that we want to wire together. Pardon me. I explained that there are 2 different ways of making this association between the ports that we want to associate with the component and the ones that that are given for the component. So the given ports are carry in, X, Y, S, and carry out. So when we're not making a named association, as is shown down below, this positional association simply associates the carry-in that exists for this design with the carry-in port on the full adder. Similarly, X0, Y0, and S0 are associated with X, Y, and S, and the carry-out port is associated with this signal C1. In order to declare, or in order to be able to use some signals that are not in the interface in our design, we have to declare these intermediate signals, these carry signals within the body of our architecture, or the declaration part of our architecture. The other way of associating signals that exist within our higher level design and the components that we want to use is to spell them out by name. And when we do that, it doesn't matter what order they appear in. The position in which they are named doesn't matter. In this case, we're associating C3 with the carry-in, C3 being the output from the previous stage. This is the most significant stage. We use this term stage usually to refer to the various bit slices they're also referred to of our design. So where we're replicating a particular design, we might talk about the stages that are being replicated. The carry-out is the carry-out that's being produced by our 4-bit adder here, and we associate the X3, Y3, and S3 signals with the X, Y, and S bits. As I say, they could have appeared in any order. This second way of naming or associating the ports with a component can be useful if we haven't, for example, sorted out yet exactly how we're going to declare this component. So we know we need a carry in and a carry out, and we know we need an X bit, a Y bit, and a sum bit, but we may not yet know what order they're going to be listed in our component. This can be tedious, of course, explicitly naming every bit that we want to add together. So the 4 bits X0 through X3 refer to a 4-bit binary number, X, as do Y0 through Y3, and the sum bits S0 through S3. So the IEEE standard, the standard logic, provides a way of using this shorthand notation by declaring a vector that we can then declare to be of a certain size, in this case having the names X3 down to X0 and Y3 down to Y0. And for the carry signal, we can also refer to those as a vector since they're all carries. But since the carries aren't really related to each other, one is the carry out of the 0th stage, one is the carry in into the 2nd stage, and C3 is the carry into the 3rd stage. We think of them not really as being numerically related, and therefore there's another way that you can refer to objects that aren't numerically related, and that is to simply use the keyword to rather than the keyword down to in terms of expressing how large that vector should be. There's no other meaning to the difference between down to and to, except one iterates from a low number up to a higher number, and the other one iterates from a higher number down to a low number. That's all that means. And obviously for numbers, this is the usual way we think about numeric values. You'll see this notation many times during this lecture, not the arithmetic one, but the next part that we'll get onto after I finish this explanation. So this is the first slide that you didn't see on Friday. The Vivado tool, like all CAD tools, provides a very large library of pre-defined components that have been optimized for the particular target technology. And if you select, I think it's called a custom component within the Vivado IP catalog, or select the Vivado IP catalog. That's one of the things that you can, one of the toolbar buttons that you have when you're describing your design. Then type in add, you'll get down to all of the adders. There's various types. But this one is a straightforward adder subtractor that happens to be selected to be unsigned. Can you read this at the back? Is that clear or not? This word unsigned. You're able to read that? Yeah, it's very blurry. I find the projector very unfocused. It's not something we can help or change though, unfortunately. So have a look at the slides. In this particular case, this is going to be a 16-bit adder, so we have 2 input arguments, A and B, that are 15 down to 0, as you can see in the way they've been described. We have this add signal, which tells the component whether we're supposed to add the 2 numbers together or subtract them from each other. And we have a carry in and a carry out and the sum that's being produced. Anyway, you don't have to worry about it any further. Once you've specified those input and output ports, essentially the tool will generate this component for you, and then you can connect it as you need to into your larger high-level block design. It's worth noting even when we simulate that design, here we have our 16-bit inputs A and B, And we can see that A is initially 0, and at time, well, it's 21 nanoseconds. You probably can't read that very easily up the back. We switch over from the input being 0000 to 3 FFFF. So all but the most significant bit being ones. It takes, though, the adder some time to shift over from summing together 0 and 1 to summing together 3 FFFF and 1. You can see here there's a period of glitching before finally the sum settles down to 4000, which is the desired result. But the time that it took from when you change the input here at 21 nanoseconds to the time that the glitching stops at 24.285 nanoseconds, I think it is 3.285 nanoseconds. So there's a substantial delay even with these library components that are optimized before the result settles down to the final desired result. And this suggests to me that the implementation of that design is using a ripple carry addition, because it takes some time for that output to settle down. All right, there are other ways that you can specify an adder in VHDL. We've looked at the structural way of doing that by you specifying exactly how you want that adder implemented using subcomponents. But we can take a behavioral approach instead. So here, all we need to do is add the vectors x and y together to produce the result s. How's that possible? Well, we need to include another package, namely the standard logic signed library, or indeed the standard logic unsigned library package, to be able for the tool to know how that plus should be implemented. But once we've included that package, the mathematical operations of addition, subtraction, and multiplication are usually fairly straightforwardly synthesized. Division is a little bit more complex, so one doesn't usually have a library definition for the division operation because it is a more complicated design. But we will get onto division later in the course. So this is obviously a lot easier for us to specify. All we need to do is worry about how large the inputs and the outputs are, and the tool does the rest. So the synthesis tool will synthesize the correct sort of IP component that it needs to be used to add operands of those sizes together. All right, so if we use this behavioral plus, then we don't actually have access to the internal signals. We don't know what the carries were, right? So that restricts us to some degree because we can't, for example, then determine whether an overflow occurred or not, which is a bit of a worry. So if we want to know whether an overflow was generated or not, then we have to access those carries that are coming into the most significant bit position and out of the most significant bit position, whereby the most significant bit, if it's a signed data type, is of course the sign bit. If it's an unsigned data type, then it's just the most significant, the leftmost bit of our arguments. So here the unsigned package is being used, so we're talking about unsigned addition. Our operands x and y are 16-bit. The sum is meant to be 16-bit, and we're going to generate an overflow signal as well. Now, in order to capture the carries, we've played a few tricks here. So we need to know what the carry into the most significant bit is and the carry out, because the exclusive OR of those two bits is going to tell us whether an overflow occurred or not. So we use a 17-bit intermediate vector called sum here, 17-bit signal, if you like, and extend the arguments x and y by 1 bit on the left. This is sort of a concatenation that's happening here on the most significant bit, and adding in the carry in, of course, because that's required. This might be part of a larger adder, so we've always got to be adding the carry in as well. Then the output sum, this S up here, is just the least significant 16 bits of the result. That's clear. The overflow, however, Well, we need to know the carry into and out of the bit position 15, the one that's nominated to be 15, right, in our original vectors up here. So this is the carry out here, because we added together 0 and 0 effectively, so the only thing that's coming into that is the carry out from bit position 15. So this is our carry out, and the rest of this expression here, x15 exclusive or y15 exclusive or sum 15, is just the carry in to that 16th bit position, because that's the carry out that's coming out of that bit position. This might not make sense that we can derive carry 15 like that immediately, but you might recall that when we were adding 3 bits together, that a carry was generated when we had an odd number of inputs being 1, right? Is that true? No. No, it wasn't. It was the majority function, right? Hang on. The sum was going to be 1 if we had an odd number of inputs that were 1. If xi, yi, or ci, if the 3 of those bits, if there was an odd number of them that was 1, we would have a sum bit that was going to be 1, right? And we derived that by saying that the sum bit is equal to exclusive OR of x15, y15, and c15. That told us whether it was an odd number or not. But that's sort of a, I don't know whether a symmetric's the right word, that we can replace any two, we can exchange, pardon me, the sum bit with any other argument. Because if the sum is 1, and there's an even number of 1s in these two, then the carry in must have been 1 as well, right? Because that's the only way that we could have got a 1 as the sum. And so we're just turning the argument around, where originally we were after the sum bit. Sum was defined as the carry in exclusive or xi exclusive or yi, because that tells us that there's an odd number of bits there to give us a sum. Well, this is the same as saying that ci is equal to si exclusive or xi exclusive or yi. Okay? I hope that's clear. Doesn't matter which 3 you take over here. If there's an odd number, you're going to get a 1 over there. All right. Any questions on this? Yeah. Nothing really to it. All we're doing is adding a 0 at the left-hand end. So this is a 17-bit 17-bit signal, but x is a 16-bit signal. So we're just making that 17th bit 0. So the ampersand is a concatenation operator. Okay? Right. Any other questions? Okay. Right. What have we got on this one? We could also use integers rather than standard logic signals. Now, integer is an inbuilt data type within VHDL, and we specify what range of we want to cover with our integer to indicate to the synthesis tool how many bits do we need to use to represent that integer. Just saying integer doesn't tell us how many bits we're going to be using, okay? But if I say from minus 32768 to 32767, that'll be a 16-bit signed integer, okay? So this, by specifying the range, we define that this is 16 bits, and again, we can just add the two together. All works. We don't need an IEEE, we don't need to include the IEEE library, we don't need to use IEEE standard logic package, because integers are built in, so we don't need those first two lines up the top here. The only thing is, there's no way of accessing the internal signals, okay? We can't just ascribe this to a different value and then access those internal signals very easily. All right, so far so good. Now, we get on to something that's a little bit hairier, or will cause some of you, I think, a little bit more trouble. We've talked a little bit about the delay through gates, which comes about because gates are electronic physical objects that have an associated capacitance and an associated resistance with them. And due to those electrical properties, we're going to have some time constant associated with the way that the gate will charge up. It will take time for the gate to charge, and it will take time for the gate to discharge. It can't be like a very sharp square wave input. While we can have an input, a driving function being a square wave, the response is not going to be a square wave. It's going to be very much curved at both the trailing and leading edges. All right, so I'm saying here that in the case of the adder-subtractor circuit, there's the longest delay is along the path from the input Y0 through X0 and through the carry circuit of each adder. So let's have a look just at which slide we're talking about. That's this guy here, where we're making an assumption, I guess, that the internals of this adder-subtractor is actually a ripple carry adder. So let's just remind ourselves of what that looks like. Where is the ripple carry adder? Up here, fair way back, where we have a full adder at every bit position, and it's the carry generation. We have to wait in every bit position before a carry in arrives before we know exactly what the sum bit output should be, because that sum, according to this equation, is given by the carry in and the two bits that are being added together at that bit position. All right? Any questions? All clear on that? So just going back to this adder-subtractor, the longest path, or the longest delay, is going to be through the least significant bit input over here, B0. So it's through this exclusive OR gate, and then from B0 through all of the carries that are in here until we've got the final carry into the most significant bit position, and that allows us to generate the sum that's there. Okay? Okay. Right. Where were we? We were up here at performance issues. Right. Okay. So that's just making the observation of what the longest path is. So we call the delay that exists within that adder, or within any circuit, the longest delay is called the critical path delay. That's just the latency that it takes, or that exists for electrical signals to get from the inputs to the outputs. And that's the maximum of those. That's called the critical path delay. And the path that causes that delay is called the critical path. Okay? So we can achieve better performance by using faster circuits ultimately. And you can achieve faster circuits in two ways mostly, is how things work. You can have a better process technology, so reducing the size of the transistors in chips has over the past few decades always led to faster circuits, because by doing that we shrink all of the wire lengths and we shrink the size of our circuits. Therefore, it takes less time for the speed of light to get from one end to the other end, or the speed of the currents that exist within the circuit to get from one side to the other side. The other way of improving things, and you will know about this as well, is that as we found with chips, eventually they're getting way too hot, and there's a fundamental limit to how quickly we can compute things if we're only operating on 64 bits at a time, is to think about restructuring the circuit. And in chips, we went from single-core processors to multi-core processors because that allowed us to do more work effectively in any one clock cycle. So let's have a look at how this technique of architectural reorganization or innovation can help us as far as our adder is concerned. So the carry propagation delay can be reduced by evaluating those carry-ins more quickly. So how are we going to do that? Well, let's have a look again at our full adder circuit. This is it over here. The carry out, or the carry into the next bit position, was given by this expression here. So if either, it's essentially sort of the majority function on 3 bits, if either both the input bits are 1, or one of the input bits and the carry in is 1, then we get a carry out, is what that first line there says. Right? Now we can rewrite that by factorizing the xi and yi out of the ci term here, and write this expression in the following way, where we're going to say that this term xi yi, or xi and yi, we're going to call that gi, because when this is 1, we can say that in this bit position we've had a carry generated. On the other hand, the other two terms, these two, one of those might be 1 when either xi or yi is 1, because in that case, when either one of those is 1, a carry in is going to be propagated to be a carry out. Right? So we're distinguishing between generating a carry and propagating a carry in the current stage. And so we can define these two functions, gi as just being xi and yi, and pi, which is, denotes the propagation of a carry, as being xi or yi. And so it's a simple tweak on the structure, but effectively what we're doing is we're leaving the blue AND gate, which is the generate AND gate, there, and we're rewriting these two AND gates as being an OR gate followed by an AND gate. So that's the simple modification that we're making. Now that doesn't look like very much yet. But let's have a look at this a little bit more closely. This is a recurrence equation, right? We can replace Ci with the expression for Ci. And that's what's being done here in this second line. We've replaced Ci with Gi minus 1 or Pi minus 1 and Ci minus 1. So the carry into the previous stage, if it's propagated or if the previous stage generated a carry, then that's what Ci effectively is. So this is that expression, and we can keep on going until we end up with C0 there in that leftmost bit position. So this is the complete expansion that we get of all of these terms if we kept on replacing Ci, Ci minus 1, Ci minus 2, Ci minus 3, all the way down to C1. Because then we get to C1 is defined as G0 or P0, C0, right? So this is the expression that we then get. So essentially what this expression says is that a carry is generated by the ith stage into the I plus first stage if we have a carry into the overall adder and every stage propagates that carry. That's one way that you could get a carry out of the ith stage. Or we could have a carry generated in the least significant bit position and have that bit propagated all the way out to the ith stage, right? Or there's all the other intervening stages that could have generated a carry and propagated that. So these are all of the possible contributions to Ci plus 1, except for this very last one, that the ith stage could have also generated a carry. I hope that's clear what that means and how you see it. I'll show you what that means diagrammatically in a moment, but for the moment just appreciate that if you keep expanding this recurrence until it terminates, then that's the expression that you get. And really all we're doing is adding together all the possible contributions to a carry out of the ith stage. Is that clear? The key thing to realize about this expression is that it's a two-level and/or expression, right? We're adding together GI with, or we're ORing it with PI, GI minus 1, and we're ORing that together with PI minus 1, GI minus 2, etc. Each one of these concatenations is an AND gate, and it's just one big OR gate, right? Got a lot of contributions to it. The cost might be high, but it's a two-level circuit. So the delay in that is simply two levels of gates, one AND gate and an OR gate. Are we clear on that? Given that we know all of the GIs and PIs, which are given by XI and YI for the GIs and XI or YI for the PIs, given that we know all of those already, and by the way, it only takes one gate to figure out what the GIs and PIs are, then we have a two-level circuit that takes the C0 input, the carry into the overall adder, and determines any carry out in two gate delays. Whereas previously it was linear. So if we use this expression to build our adder, then that's called a carry look-ahead adder. So let's have a look at what that looks like as a circuit. So here's pretty much our original ripple carry adder, except we've made that replacement. We've got the GI and PI, and therefore we have that second AND gate. So we replace one AND gate with an OR gate, and we have our other AND gate here. ORed those together to create the carry out. So we're using this expression here. At every stage we're using this expression. The carry out here is equal to G0 or P0 and C0. The carry out here is equal to G1 and P1 and C1, right? So the critical path length in this case, as shown in red, is going to be 2n plus 1 gates, because it takes us one gate delay to compute the G's and P's when all the X's and Y's are presented in parallel. It takes one gate delay. So all of these are determined after one gate delay. But then it's two additional gates in every stage that we have to go through to get the next carry, right? So the carry out of the most significant position is going to take 2n plus 1. So for Cn, it's going to take 2n plus 1 gate delays. So each stage is just adding two gate delays, right? That's what we had previously, effectively. Now let's have a look at what happens if we use this expanded expression where we've recursed all the way back down to the base condition where we know C0 and nothing else. Well, we still produce our GIs and PIs in one gate delay, right? But the circuitry now looks a little bit more complicated, right? I claim that in this circuit, all carriers are generated at the same time after 3 gate delays. 1 gate delay for the GIs and PIs, and 2 gate delays, what we see in gold here, to produce the carry out, right? I didn't need to know the carry out here in this stage to produce the carry out of this stage, right? Because all I need that carry for is to determine what the sum is. It doesn't need to be propagated any further. All sum bits are computed in 4 gate delays because the carries are computed after 3 gate delays. Then we have an exclusive OR gate, so that makes the 4th gate delay. Forget about the fact for the moment that exclusive OR is actually a longer gate delay than 1. It's probably more like 3 or 4 gate delays. Doesn't really matter. It's a constant number. Once I know C, I get the sum in a constant number of gate delays up. But the complexity grows at every stage, and this is really important to appreciate here. Well, it comes from this expression, right? We get 2 additional wires coming out of each stage. This stage had 4 wires. This guy has 6 wires because we need the GI and PI to send that to the more significant stages, right? So 2 additional wires get added to the output side for each stage. I've got 1 more AND gate with 1 more input added per stage. So this stage only had a 2-input AND gate and a 2-input OR gate, right? This guy has 2 AND gates, and apart from the 2-input AND gate, we've got a 3-input AND gate here. How does that come about? Well, that happens to be the C0 and P0 and P1, right? Both of which, so that's that last term that we have over here. That has to go into our OR gate in order to produce the carry out for the next stage. And finally, there's 1 more input to the OR gate per stage. This guy has 2 inputs, this guy has 3. The next stage will have 4, and so on. Every stage will keep on increasing. So we've got more and more terms to consider in this expression. The bigger I is, the more terms we have to add together, right? So the complexity grows from every stage. 2 more wires, 1 more AND gate, 1 more input to that AND gate, and 1 more input to the OR gate in every stage. Obviously, we can't do that ad infinitum, all right? If you look up how many inputs can you have to a gate with 7 nanometer technology, it's probably 2 to 3 fan-in, max. So this is a nice architecture, but it's not practical the way that it's illustrated here. But let's not worry too much about the practicality for the moment. What I need you to understand is the structure and what the implications are of implementing this equation. It does allow us to determine the carries after 3 gate delays for all stages, whereas previously it was 2n plus 1, depending upon how large n is. But each stage has to become larger. There's a linear growth in the stages, and when you look at it overall, it's an exponential growth for the size of the adder all up. So that's not so great. So as a consequence of that, because of these physical limitations on the sizes of gates, what's normally done is we implement a hierarchical design for our adder using carry look-ahead addition. We define a block of bits, in this case 8 bits per block, are going to be added as a CLA internally, right? And then you have to figure out, well, what do you do about the carries? Should we just let them ripple from one block to the next, as we did with the full adders previously, which is the design that you see here, or an alternative, which is illustrated here, is to take sort of group generate and propagate signals from every block, and I'll define what they are in a moment, and then have another level of carry look ahead down below. Obviously this is not desirable either, but it makes for quicker determination of what the intermediate carries are. Because if we rely on the ripple carry design that we show here, there's still a linear growth in the delay, in the latency in generating these carries. Whereas if we use a second level of carry look ahead, it might be larger than we saw in that first theoretical slide of how carry look ahead is implemented, but we can then generate these carries at the same time in parallel, albeit with a slightly larger delay than we saw previously. Before going into the details of that any further, let's just have a think about what the delay of this design is, let's just focus on this block 0 here. So what's happening inside block 0 is that this circuit is being implemented. So we know that all the carries are created, are determined after 3 gate delays, right? 1 for the GIs and PIs, and then this 2-level and OR circuit gives us what the latency is for each carry. And after we know what the carry in is, then, well, after 4 gate delays, the sums are determined. So, in this block, we know that the carry out is generated after, or is created after 3 gate delays. So once we know the X's, Y's, and C zeros, 3 gate delays later, C8 is known, all right? And after 4 gate delays, we've got all of the sums produced out of this block. But if C8 only arrives after 3 gate delays at block 1, and we have another 2 levels, a 2-level and OR circuit to determine C16, then C16 is going to be available after 5 gate delays, C24 is going to be available after 7 gate delays, and C32 is going to be available after 9 gate delays. So it's linear in the number of blocks that we have that tells us what that carry is going to be. And the sums are only going to come out 1 gate delay after that last carry. So it takes us 10 gate delays to get these bits out. Yeah?
Did it only increase by 2 because we can compute the GIs and PIs before?
GIs and PIs can all be computed, but that's only 1 gate delay, right? So what happens is, while it takes us 3 gate delays to get this guy, it only takes us 2 more to get this guy. Right, good. Any other comments or questions? Yeah?
We still have to wait until the last carry out comes out?
Yeah, we do. So, but that's not the critical path. The critical path, or rather even the critical path delay. That guy comes out after 9 gate delays. We need to wait till, well, this guy comes out at the same time as all of the intermediate carries are generated in here, and we can only compute the sums after we know that. So there's still that exclusive OR gate that we need before we can compute the sums. So we're saying 10 gate delays for the sums. So that's the critical path delay. All right, so let's have a look at what this structure means. And in this case, note that there's no wire that connects block 0 to block 1 directly. Rather, we have this G0 and P0 wire coming out, capital G and capital P. For block 1, same thing, we've got capital G1 and P1, and no direct connection between block 1 and block 2. Rather, we have these blocks of logic down here that implement a carry look-ahead circuit and produce the carries out. So we have C0 coming in, G0 and P0 coming in, C8 gets produced. In this one, we have C0 coming in, we have the G's and P's, both G0, P0, G1 and P1, and we have C16 being produced, etc. Right, so what do those capital G0s and P0s look like? Well, they're just the group generate and propagate signals, so they're effectively the terms of the expression that we had before for C8 re-expressed. So G0 is really just all of the terms in here except for the very last one that involves C0, because that is P0 over here. It's all of the P's, the internal P's, ANDed together. It gives you P0. All of the other terms that involve the G's, the GIs, G0, G1, G2, all the way up through G7, are incorporated in G0 here. So that's the expression for those group generate and propagate signals that we have. Here's the expression for C8. Again, it's a 2-level circuit though, right? We had to wait for the GIs and PIs to be generated, to be created. Then we have a 2-level circuit to generate or to create G0 and P0. And once we have those, it's a 2-level circuit to get C8, right? So it's 3 gate delays to get G0 and P0, and 5 gate delays to get C8. Similarly, though, to get G1 and P1 is also 3 gate delays, right? And this is also a 2-level expression involving C0, P0, P1, G0, P1, and G1. So while it was 3 gate delays to get the G's and P's here, it's 5 gate delays to get C16, C24, and C32, right? Each of them only takes 5 gate delays now. So just looking back at this, it's 5 gate delays to get C8, 5 to get C16, and 5 to get C32 ultimately, right? But that's just the carry in to each of these blocks. Remember that there's still 2 more gate delays there internally to get the individual carry bits within the block, and then 1 more gate delay to get the sums. So while it takes us 5 gate delays to get the individual carries into a block, it's another 3 gate delays to get the sum bits out at the very end, out of each one of these blocks. So overall, it doesn't really matter that if you kept on going with this, you could, keep on increasing the size, but the principle here is that it's a fixed number of gate delays to get the SIs and the CIs out of there, as opposed to the design that uses the ripple carry here, where it's a linear increase in the delay to get the C's out from between the blocks and also to produce the sum bits that we have. Right, so overall, I guess I've just really summarized what happens overall here on this slide. But we're making huge assumptions here about how big a gate can be in terms of the fan-in without seriously impacting the speed of the gate. And normally, for high-speed circuits, you probably wouldn't want to have a fan-in of more than about 2 or 3. Therefore, you have to go to a hierarchical circuit expression for each one of these very long expressions. So for this expression here that has 8 inputs, you'd need to build a tree to get that and calculate it. All right, good. So in practice, you need to, it's more complex to design the circuit. The circuit is explained in the text. If you'd like to read more about it, I don't think it's necessary. I wanted you to get a feel for what sort of thinking needs to go into how you restructure a circuit to make it faster. And there's a take-home message here as well. Generally, to get fast, you have to throw lots of hardware at it. So usually there's a trade-off between speed and circuit size. So if you want a fast circuit, you're going to have to use lots of hardware to do it. Yeah, that's a general cost. Parallelism involves doing things with a lot of hardware in parallel. Okay, so I can imagine your head must be about exploding at this point in time. So I actually had an interlude planned for you while you have a break. Are there any questions on this before I go to the interlude? I've obviously blown your brains. I don't know how well this is going to work, because it always makes me think about this song for some reason or other. Can you guys hear at all? How many know this song? Anybody? That's because it's from 1982 and you weren't born. It's a pity that the sound doesn't come out. Right, this doesn't seem to work so well. Put your hands on your head. Look, this album, Big Science by Laurie Anderson, it's a brilliant album. There's nothing significant about the song, but you know, when your head blows like this, you think, put your hands on your head. So that's why it reminded me of this song. But there was some comment about it that I was reading up this morning when I found the album. It was sort of interesting, actually. I can't seem to find it. It was sort of an explanation about the song a little bit, but I'm not sure whether it was accurate or not. These are just the lyrics. No, don't know. Right, are there any questions about what we've talked about here? Okay, we'll move on to the next lecture then. All right. As I foreshadowed, we're moving on to combinational building blocks, whereby what we want to do here is learn about commonly used combinational subcircuits. Specifically, we'll talk about multiplexers, which I've already introduced to you, but we'll go into more detail, encoders, decoders, and code converters. Today we'll also talk about non-simple concurrent assignment statements, but we won't talk about sequential statements until Friday. And we'll look at how to use Shannon's expansion theorem to implement Boolean functions on Friday. Okay, so we have actually seen this guy before. I talked about the two-input multiplexer that looks like that in the context of a two-input lookup table for selecting a particular memory cell to be out of that lookup table. But let's generalize that a little. So a mux has a number of data inputs, in this case 2, and we use the selector to determine which one of those inputs is going to be routed through to the output. Truth table's given here, so it should be fairly easy to see just by inspection that when S is 0, the function output is the same as W0, and when S is 1, the function output is the same as W1. So this is like a condensed version of that truth table, and obviously then the circuit diagram looks like this on the right, because we're expressing this function that we have here. All good? So a 4-to-1 mux is going to have 4 inputs, and if you're selecting from amongst 4 inputs, you need 2 select bits. So hence we have 2 selectors coming in here. Pardon me. And the following truth table is being implemented. So depending upon the value of S1 and S0, the corresponding input, W0 through W3, is going to be routed through to the output. This is the function that's being implemented. So when both bits are 0, it's the W0 input that's being routed through to the output. When we have binary 1 being represented by the select bits, it's W1 bit that gets routed through, and so on. We can keep on building larger muxes this way, but it's more common to build them up from smaller muxes. So for example, we could build the 4-to-1 mux from 3 2-to-1 muxes in this way. Now you've been building 3-to-1 muxes, haven't you, in the lab? Yes, good. So you have already seen some of this. In this case, the select bit S0 determines for the least significant muxes here in this tree of muxes which bit is to be routed through onto the intermediate signals, X0 and X1. And then the more significant select bit determines whether it's the X0 value or the X1 value that gets routed through to F. And we can easily then derive that it has the same functionality as the 4-to-1 mux did that we saw previously. We can keep on going in this vein and build a 16-to-1 mux from 4-to-1 muxes. Here, each mux at the leaf level is a 4-to-1 mux. And we're going to assume from now on that the inputs to muxes, when we depict them, are generally numbered from 0 up the top down to, well, to the n minus 1 down the bottom for n select bits, right? Okay. Where are muxes used? Well, we've seen one use, which I'll get to in the next slide, but here's another use in switches. They're often used to implement what's known as a crossbar, whereby any input can be routed to any output. And we could use two input muxes wired up like this to affect the ability that either X1 and X2 have the straight through connection to Y1 and Y2, or that they cross over in this switch when S is set to 1. We didn't talk about this when we looked at FPGAs, but we did talk about the fact that you have vertical wiring channels that allow the lookup tables to be connected together to create larger functions. The crossovers between the inputs for a particular lookup table and the wires that are running vertically or horizontally in the FPGA, they're known as connection boxes. They can be implemented a number of ways. So this is for determining which one of these vertical wires should be routed through to I1, and which one should be connected to I2. So one way of creating that sort of structure is to use pass transistors that short circuit the connection between a vertical wire and the horizontal wires that we see here. In that case, each pass transistor has to be programmed to determine whether that transistor should be closed or open. And in fact, you only ever want one closed transistor here, because otherwise we would get a short circuit between vertical wires, which of course we don't want. We only want for each horizontal wire, we want it to connect to one and only one of the vertical wires that we see in this design. On the other hand, if we choose a mux to implement this connection, then we can reduce the number of storage cells that we need to program the connection. And we also guarantee that now we will only ever be using those inputs as the output here, because the mux is designed that way. It can only route one of the inputs through to the output. All right, so this saves us significant storage space, and it ensures that we don't get cross connections that would be potentially harmful for the FPGA device. What we'll see later on in the lecture is that we can implement functions with muxes, and we saw this to some degree because we looked at the 2-input lookup table that had 4 storage cells that we could program with any bit pattern, and in this case we can see that the exclusive OR bit pattern has been wired up to the mux. So depending upon the inputs W1 and W2, the output will be 0 or 1 based on whether or not there's an exclusive OR between the inputs W1 and W2. We can actually be more efficient than using a 4-to-1 mux. We can get away with, in this case, just using a single 2-to-1 mux. And that is because in the upper half of the truth table, when W1 is 0, the output is just the same as W2. And in the lower half, when W1 is 1, the output is just the complement of the input W2. And so we have this relationship that we see here in this condensed truth table, which can be wired up as we see down here. So we really only need a 2-to-1 mux to implement that exclusive OR between those 2 inputs. Another example here, the 3-bit majority function, which is going to be 1 whenever a majority of the 3 input bits is 1. Well, we can use 2 of the inputs to determine which selection we want on the mux, and the third one should then just tell us, well, what's the value of the function at that particular point? When W1 and W2 are both 0, the functional output is 0. When it's 0, 1, the functional output should be the same as W3. W3 again down here, and then finally, whenever W1 and W2 are both 1, the function should be 1. So this is the way to wire up that function within a 4-to-1 mux if we want to implement it. So we can generalize this, and we'll look at this later on in the lecture. It's called Shannon's expansion theorem, that teaches us or tells us how to make most effective use of muxes to implement any arbitrary function. We want to look a little bit more at these components initially. So beyond muxes, we're going to look at decoders, encoders, and code converters. So a decoder, which is illustrated here in this block, has n inputs plus an enable signal, and these n inputs, depending upon the pattern of inputs that we have, will select one of 2 to the n outputs to be asserted. So it's the code that is represented on these n inputs that is then expressed as a single wire being asserted on the output side out of 2 to the n possibilities. How is that implemented? When the enable is 1, it depends on the bit pattern of W0 and W1 as to which one of the output wires is asserted. There's just that relationship between the binary value of the inputs and which wire it is by a number that is asserted on the output side. When the enable bit is 0, none of the output bits are enabled here. So it's relatively easy to see how that's then implemented. There's another tidbit of fact here, another factoid about decoders. The output here, since there's only ever 1 bit that's being asserted, we say that the output is 1 hot encoded, except when the enable is 0. Then there's no bit that's enabled, so it's not really true when the enable bit is deasserted. As with muxes, we can use smaller decoders to build larger ones. So let's have a look at building a 3 to 8 decoder. Here we have 3 input bits and 2 to 4 decoders that are wired up in this manner. So the less significant bits of our input determine which one of the 4 output bits is going to be enabled when the corresponding enable signal is asserted. But that is controlled by this input bit W2. When W2 is low, then the upper enable is going to be asserted, and when W2 is high, the lower enable is going to be asserted when the enable to the overall decoder is asserted. So you might see that this input circuitry that we have here is really just a 1 to 2 decoder. Okay, even larger, a 4 to 16 decoder. Again, the less significant bits determine which one of the 4 outputs of the 2 to 4 decoders get asserted, and the upper 2 bits are used within another 2 to 4 decoder to drive the enable signal on the corresponding decoder. We can use a decoder to create a mux. Here's our decoder. It has the select bits driving the W0 and W1 inputs, and the enable's always asserted so that we're always getting one of the W0 through W3 inputs being routed through to the output F. But the decoder is just generating all the logic we need to steer these AND gates. This is probably more for the computer engineers that are in the room. We can also use something that's known as a 3-state buffer, which allows us to wire together all of the outputs, assuming only one of these 3-state buffers is enabled at any one time. We use a decoder to enable the 3-state buffers, but effectively this also works as a mux then. The buffer, when it's asserted, passes its input through to the output. When it's deasserted, it's just an open circuit. Not too important from a theoretical perspective at this point in time. Another use that we can put decoders to is to so-called demultiplexer signal. So we saw that a multiplexer allows us to choose which one of 2 to the n inputs should be routed through to the output. The decoder does the opposite. So it does it in this way. If we have a mux on one side selecting between 4 inputs, routing that onto a wire, if we make the same selection on the output here, on the input to the decoder, it will get routed through to the corresponding output that we have over here, Y0 through Y3. That's under the assumption that the select bits here are being coordinated, so they're driven at the same speed or at the same time to have the same input and output. The benefit of doing this is that we only need one wire then to communicate between 2 distant points, let's say, using effectively by dividing our time amongst the 4 possible inputs there, time division multiplexing. So that allows us to concentrate the data that's appearing here on these 4 inputs onto one wire, communicate it over a distance, and then send it back out on the corresponding wire on the output side. Another use decoders are put to commonly is to address a memory block. Here we see an M to 2 to the M decoder being used to decode an M-bit input address, which selects one of 2 to the M select lines here that drive this memory array over on this side, which we can then read the corresponding memory line from and out of the memory using buffers, 3-state buffers here that are connected to a read line. None of that's really important. What is important is that the decoder can be used to address a particular row in our memory, and that's a common use for a decoder. Any questions on decoders? I feel I'm stretching you already. Who's awake? Uh-oh. Who's not awake? Don't know why you put your hand up. All right. So it is a bit dry, this part of the presentation, I have to admit. We're still going to talk about encoders, the opposite of a decoder. And then we'll get on to some VHDL, which won't be all that much more exciting, but we have to push through that so that you have some more background for your labs. And then we'll leave it. I'm hoping that we'll get this done in about 20 minutes, 20 to 30 minutes max. So you'll have an early mark. All right. Yeah, I've got possibly another 15 slides to go or so. So we've looked at decoders which took an n-bit input and selected one of 2 to the n output wires to assert corresponding to the code on the n input wires. The encoder does the opposite. It takes one of 2 to the n inputs and encodes which input it is that's active on the n output wires. All right? For that to work, in theory, you only want one of these 2 to the n input wires to be active, because then you have a clear indication of what the code should be that has to go onto the output. If there are multiple inputs that are active, then we can define what's known as a priority encoder, and I'll show you that in a moment as well. So here's the circuit for a 4 to 2 encoder. Here's the truth table for it. So depending upon which input wire is active, we have the corresponding code put onto the output. That's effectively what it says. It's a bit of a strange circuit because W0 isn't even connected to anything here. So that's not very helpful. And it's not really clear from this table what you're meant to do if no input is asserted, or if more than one input is asserted. So I don't really like the specification for this encoder very much at all. I think they do a better job of explaining how a priority encoder works, which is given by the truth table that we see here. In this particular case, if no input wire is active, then it doesn't matter what code we put on, but this Z bit tells us that no bit was active. However, if at least one bit is active, then the Z bit is high to tell us that a code did arrive. Now, because it's a priority encoder, it's possible that we have more than one wire being asserted. So what the code tells us here is what's the most significant bit that's being asserted. So when only W0 wire is being asserted, it's the most significant bit, so it's 0, 0. When W1 is asserted, and it doesn't really matter whether W0 is or is not, then we're going to put 0, 1 as the code, the output code. So the code represents the most significant bit that's 1. Right? Can think of it as the leading bit, telling you which is the leading one. Okay, so we could use the usual methods for figuring out how the circuit should be designed. The text suggests using a different approach, namely to define these 4 intermediate signals, which effectively tell you what's the leading one. So I0 is 1 when you have a 1 here and the rest of the bits are 0. I1 tells you that there's a 1 here and the other leading bits are 0. I2 tells us there's a 1 in this bit position and the other bit is 0. And I3 is 1 when W3 is 1. We don't care about the less significant bits. And then it's easy to encode the code that we have as the output, because now we can see that I0 should be 1 when we have, well, it's either in this row or this row, i.e. when we have I1 or I3 active, right? And I1 should be 1 when we have either I2 or I3 active. And Z is going to be active when any one of those codes is active. Otherwise, it's 0. Okay? So that's sort of useful. So we've talked about muxes, decoders, and encoders. More generally, we normally need to do what's known as code conversion. We go from one code to a different code, and it's not always a unary to a binary or a single input to a binary output or a binary input to a single output. There's more general codes that need conversion. For example, let's say that we're driving a 7-segment display. This is something I know you're already familiar with. Then we need a box that converts. In this case, we want to represent on the 7-segment display any one of the 9 or 10 BCD digits. These are the 10 BCD digits that exist. They correspond to the binary values 0 through 9. The code for 10 through 15 isn't used, all right? They're not valid inputs to this code converter. And so depending upon which input code we have, this table tells us which segments are lit up in the 7-segment display. Now it's actually the opposite of what you've got in the lab, because in your case, you need to drive the segment with a 0 in, pull it low in order for it to light up. And it's a 1 if it's not lit up for a particular digit. So think of this as being the complement of what you're meant to be computing. But then we can easily derive, the function that tells us when is segment A lit up. We can derive the function that tells us when segment B is lit up, etc. And we'll need 7 functions there to light up those 7 segments, okay? How do you do that? How do we figure out what that function should be? How? K-map, great. How big?
4.
Okay, 4 input bits. Are we going to have every cell containing a 1 and a 0? Somebody else? Will every cell in our 4-input K-map have either a 1 or a 0 in it? Sorry?
Yes.
Who agrees? Nobody agrees with you. So what could it be other than a 1 or a 0?
Doesn't matter.
Don't care, exactly. In our case, we're given 10 rows where we know that we have a 0 or 1. In the other 6 cells, we write a D because we can use it either as a 0 or as a 1, right? Yeah? Correct. How would we map this row into our 4-input K-map? What's going to be the row? Sorry, what is going to delineate the columns? Which variables? X3 and X2, right? And we have X1 and X0 labeling the rows. Right, and then we have 1, 0. So I'm doing A bit here. 1, 1. Then we have 0, 1, 1, 1. 0, 1, 1, 1. Then we have 1, 1. And the rest is D. Right. What's cheaper, SOP or POS, when you minimize it? Why? You're just guessing.
There's less zeros and ones.
Well, there's D's over here. So if we went for POS, I assume you'd combine this D together with that 0 and you'd be left with this 0, right? What's the cost? Who was it that said POS? Who am I talking with? Yep, okay. What's the cost of that? It's one 3-input gate. here, one 4-input gate, and one 2-input gate.
Yeah.
So what's the total cost? 3 gates plus 4, 3, 2, plus 9. 3 and 9 is 12, right? Is that right? 4, 3, and 2, yeah. 4, 3, 2, 4, 3, 7, 9. Yes, so it's a cost of 12. Righto. What about the SOP? How would you do the SOP? This is the POS. Righto. All of this, right, which corresponds to x3, x2, x1, x0. Did I get that the wrong way? Yeah, that corresponds to x1, right? Or right, we want the right half here because we've got to cover that one. This one can be combined with that one, right? What's the right half? Yes? Now we've still got this one and this one. How do we cover them?
A square in the middle. And then
What? When you... What? Ah, I'm glad somebody said that. All the corners. Sorry? Right. What are all the 4 corners? What's that term? I'll save you the trouble. Right. So we've still got this one. Square in the middle, which is? Save you the trouble. Right, what's the cost of that? So it's 2 2-input gates plus 1 4-input gate, right? Am I right? Because I've got to AND it with x1, or with x1, x3, not x2, x0, and x2, x0. So that's 4 inputs, 1 OR. And we've got these 2 input gates. So what's that? That's 3 gates plus, that's 4 is 8. So it's 3 plus 8, which is cheaper. Good. Right. Okay. Well, so I'm assuming you're going to be doing something similar in your work. Right. Let's just quickly have a look at some non-simple signal assignment statements. So, when you see this idiom with sSelect, assign to f W0 when S is 0 and W1 when it's anything else, that's a mux that is inferred. So whenever you need to create a mux, use something like this idiom, right? All possibilities of S have to be covered. How many are there? Wrong. How many are there? What type is S? Standard logic. How many values does standard logic potentially have? 9. Apart from 0 and 1, there's unknown, don't care, undefined, uninitialized, there's weak, there's L, and there's high, right? So there's, this others catches 8 other possibilities there. Only 0 So be aware of this. This is the standard syntax, and it works when you're implementing it because you won't have W's unless you've left Y's unconnected, etc. And in the end, you get a circuit generated. You get this circuit generated, right? And if S is, well, if S is being driven to 0 in some cases, it's going to be driven to 1 in other cases. It's never, in a practical circuit, unknown. It's initialized to a particular value. Okay, so here's the 4 to 1 mux. Obviously now S is a vector of 2 bits, 1 down to 0. It's numeric here because these inputs have a value in the sense of which order are we going to associate with which combination of inputs, right? Which input's going to be connected. So whereas we use a single tick for a single bit constant, we use double quotes for multi-bit constants, as is shown here. How many conditions does others cover here? With a 2-bit vector standard logic, you've got 9 times 9, 81 possible combinations, right? You've taken 3 out, so you're left with 78 that are being covered there. Just be aware of that. Right, we might want to use a mux in other situations, so we might want to put it into our own package. Normally you would have more than one component in a package, so this is where we begin to see our 0 to 15 sort of signal. So here we have 16 inputs that are not related with each other, so we call them 0 to 15, not 15 down to 0, because that would imply W is a number. W is not a number here, it's 16 different inputs. The selector, on the other hand, is a number. Based on the value of S, we're going to choose a particular Y to be routed through to the output. Here we've included our package. We don't actually need to write the line library work because work's already defined. Work is the current working directory. So we just need to say that we want to include that package that's in our working directory, and the compiler should find it. We have to have an intermediate signal here to connect the output of the leaf muxes to the root mux over here. Let's call them M. Again, they're not mathematically related, so 0 to 3, not 3 to 0, down to 0. And then we instantiate 5 muxes as follows. I hope that's clear. Are there any questions about this design? So it's a structural implementation because it tells us how a big mux is built from smaller muxes. Hence, we call it a structure. That's our choice of word here, structure, as is mux 16 to 1. That's our word. It's not a reserved word in the language. All right. Another few tricky, intricate things that can be done with VHDL. We have this for generate term or syntax statement, which is a bit like a macro in conventional programming languages. Essentially what this says is, before you go ahead and synthesize this design, replace this, what's included in the for generate statement, replace this line with all of the lines that would occur as I varies from 0 to 3. So we're going to have a mux 4 to 1 with W0, W1, W2, W3, S1 down to 0, and that's going to be M0. And when I is 1, it's going to be 4, 5, 6, 7, and it's going to be M1 that's generated. So replace all of those lines with macro style with all of the possibilities for 0 to 3, and then go ahead and synthesize it. So it's just a way of reducing the amount of typing that you have to do, or the copy pasting that you have to do. So it's like shorthand for providing a whole heap of concurrent statements. Is that clear? We've seen the concatenation operator already. Here we've got a 2 to 4 decoder that we want to specify. Note that we're using the same syntax as we would for specifying a mux. So with the 3-bit signal, that's the concatenation of the enable bit and the 2 input W, right? These 2 bits. So it's all 3 bits together. Given that Y is specified from 0 to 3, not from 3 down to 0, it's going to be 1, 0, 0, 0 when the input is 0, 0, when the W's are 0, but enable is asserted. All right? So based on the order in which these are listed, we have to be careful about how we write our output, because otherwise you'll get an unexpected result. If we're saying Y is the bits of Y are counted from 0 to 3, as is done here, then the least significant bit is the leftmost bit, not the rightmost bit. Okay. Any questions? You'll sort this out in your own time. Building a larger decoder. Again, we have a for generate here to generate these decoders on the right here. And there's also an if generate statement, which I would never write this way, personally. I would just put this guy as a single line after the for generate statement, because it would be clearer. But here they're showing you how to use a conditional generate statement in the middle as well. Obviously, this is only going to be expanded when I is 3. Okay? So you only get 1 deck left, but you get 4 deck rights. All right, there's another type of assignment statement. So far we've seen simple assignment statements, which just assign the right-hand side value to the left-hand side. We've seen selected signal assignments, which are of the form with some signal select, and then what's the value that's going to be assigned. This is a conditional signal assignment. So we're going to assign to the output F W0 when S is 0. Otherwise, assign to it W1. Exactly the same as the mux. So this is a 2-to-1 mux specified using a conditional assignment statement. I hope it's clear from the syntax what's meant there. So again, only when S is 0 is W0 going to be assigned to F. In all other eventualities, if S is any one of the other 8 values it could have, W1 is going to be assigned to F. Here's the priority encoder using this conditional signal assignment. It's quite nicely specified this way. So we're talking about assigning a value to Y0 and Y1 based on the input that we have over here. So when W3 is 1, we're going to assign 1, 1 to Y1, Y0, and so on. Otherwise, when W2 is 1, it's 1, 0. When W1 is 1, we're going to have 0, 0, 0, 1. Otherwise, it's going to be 0, 0. All right? We've also got our Z signal that we have to worry about there. So when the synthesis tool is determining what should the logic be, it's going to evaluate each one of these clauses sequentially. But of course, the hardware that it generates is going to be running in parallel. So this evaluation of the conditions in listed order is what the synthesis tool would be doing when it's trying to figure out what hardware should be generated. It's not how the hardware operates. The hardware doesn't have a preference for saying W3, when W3 is 1, I'm going to associate 1, 1 with Y. The nice thing about the conditional signal assignment statement is that these conditions here don't have to be related together, whereas with the selected signal assignment, we've only ever got the one signal, the one select signal that is being used. And here's essentially the same thing, but using a selected signal assignment. Of course, that then is a lot clumsier than this expression here. Because now we have to be a bit more explicit about what the conditions are that lead to a particular outcome. And it's also worth noting that for the select signal assignment, all of these conditions are evaluated in parallel as far as the synthesis tool is concerned. So each one of these assignments or possible assignments is set up in parallel, whereas here we have this sequential evaluation of these conditions. I'm glad I've been able to make you have a little snooze. Are there any questions about what I've talked about? Yeah.
You said for this one, it's not sequential, but
Yes.
I don't really
So it's very importantly, it is not the hardware that's generated that's sequential. It's the tool that evaluates the statements in order to generate the hardware. There's no implication that on the previous slide, the hardware that's generated evaluates these conditions in a sequence. All it implies is that W3 being 1 is more important than W1 being 1 in terms of making the assignment. Then we have to assign 1, 1 to the output. Okay, so it's really just the synthesis tool and its evaluation as to how it processes that information to create the hardware. But the hardware operates in parallel. Remember that we had the circuit. Sorry. I want the priority encoder. Here we go. This is the hardware that we want to generate, right? Or rather, it's this truth table that we want to create. It's combinational. This is an expression for how each one of these bits is determined. So we want the synthesis tool, when we give it that code, to generate this hardware or something like it. We want it to generate a circuit that's going to create our Y1 output and our Y0 output and our Z outputs in parallel, and do so as quickly as possible. So we want those circuits to be efficient. It's not a sequential evaluation. Look, this is really the hardest thing to appreciate, that hardware operates in parallel. So if we want a language to express what the hardware does, we have to somehow, we either have to have semantics, we have to have a language that encapsulates the idea that the hardware is working in parallel, yet we're writing it sequentially. We have to read it sequentially, character by character ultimately. It's got to have a meaning, though, that says this is all happening in parallel. Whatever can operate in parallel should be allowed to operate in parallel, because that's going to reduce the latency by the most, right? So the hardest there's several things that are difficult to understand about VHDL. It's not a programming language, firstly. You're using it to describe what sort of hardware behavior you want, ultimately. But the implication, unless it's explicitly stated that one thing should happen after another, and we're going to get to that on Friday, we'll start looking at sequential code, is that everything should be happening at once. So when you say something is evaluated sequentially, we're talking about the tool that processes that code and how it understands it. And that is different from the hardware that we want to generate. And we also use that tool for simulation purposes, which again is a different thing. Then we have to understand, or the tool has to understand, for a given circuit, which bits are going to receive a signal at the same time, or could potentially be receiving a signal at the same time, and act accordingly. So you use massive event simulation tools to be able to do that. You will get it eventually, but you have to suspend belief to some degree. It's not like what you've learnt before about programming languages. Okay, I don't want to belabor the point too heavily because it's not that significant. It's better if you don't think about it too much and think, well, what's the hardware that I want? That's the hardware I want. So then, don't I want to synthesize these or something similar? Or go through the process of, you know, I mean, this is using human insight, this design, but the tool could expand this truth table to have all possible 16 possible lines and determine what the output should be, and then do a simplification of that, right? Any other questions? Okay. I reckon it'll take until week 6 or 7, and then you'll probably be clear on it. Okay? Good. Thanks for putting up with it.
From an exercise, like in the that was
For next
for this week on
yeah,
Friday.
yeah.
Because I'm confused. It said to find the
No worries.
synthesization, but I can only have a fan and a two, so I have to pick like an 8x8.
That's not the way I take it. I would simplify the expression that you're getting and then